In this module, we shall see a very convenient criteria for checking whether certain type of sequences are convergent without having any candidate idea of what the limit is going to be. First, let me begin with two definitions. The first is that of a bounded sequence. A sequence AN is said to be bounded if we can find a positive real number capital M such that mod An is less than M for all n in the natural numbers. Every term in the sequence is bounded in absolute value by the number M. The second definition is monotone sequence. A sequence AN is said to be increasing if A1 is less than or equal to A2, is less than or equal to A3, and so on. It is said to be decreasing. If A1 greater than or equal to A2 and so on. Okay, we shall employ the terms strictly increasing or strictly decreasing if the inequalities above are strict. And increasing, better way to state it is, a sequence is said to be monotone if it is either increasing or decreasing. Of course, we shall also sometimes employ the term strictly monotone to suggest that the terms in the sequence are strictly greater. I mean, A1 is strictly less than A2, strictly less than A3, so on. Okay, so now we have a very simple proposition about bounded sequences. About convergent sequences. Any convergent sequence AN is bounded, and the proof is very easy. Suppose AN converges to A. Since the sequence is convergent, it must have some limit, let's say A. Set epsilon by definition equal to 1. Then if small n is greater than n epsilon, then mod An minus A is less than 1. Right? That's the very definition of this n subscript epsilon. That is, whenever the number small n is greater than n epsilon, the terms of the sequence AN must be at the max epsilon close to the limit. Here epsilon is 1. Okay. But by the reverse triangle inequality, this is just saying mod An minus mod A is less than 1. In other words, mod An is less than 1 plus mod A. Okay. So it seems like we have already satisfied the definition of bounded, but not quite. This final inequality mod a n is less than 1 plus mod a is true only for those terms of the sequence that are beyond n epsilon. Okay, what you do is you set m to be mod a1, mod a2, so on up until mod a n epsilon. Then you add 1 plus mod a to this list. You take the maximum of all these quantities. You take the maximum of the absolute value of the first term, the second term, the third term, all the way up to the a n epsilonth term, and then you just put 1 plus mod a, because anyway mod a n is going to be less than 1 plus mod a. Then clearly mod a n is less than m for all n and n. That's how this capital M has been constructed. Okay, and we are done with the proof. Now we come to the important theorem that says bounded monotone sequences are convergent. And increasing sequence an that is bounded is convergent. Now the motivation for studying this monotone sequences is the previous proposition, which says that convergent sequences must be bounded. So our guess would be that bounded sequences are also convergent, but that is clearly not true. Think of a counter example yourself. The next best thing is to say that at least monotone sequences that are bounded will be convergent. Now I have here stated it for increasing sequence. Think about how you can prove the same thing for decreasing sequences. Proof. Now, to show that a limit exists, we need some candidate. Now, what is happening? This sequence is increasing, but it cannot increase beyond a particular point, capital M, simply because the sequence is bounded. So, what we will do is we will set A to be the supremum of all the ANs. We are putting all the ANs as a set, and we are taking the supremum, and this supremum exists. Why? Because of completeness. Exists because of completeness. Okay. Now our candidate for the limit is obviously going to be the supremum. It is the least element such that no element in the sequence an exceeds it. So it's a very nice candidate for the choice of limit. Fix epsilon greater than 0. Okay. Now recall the equivalent characterization of supremum as that for each such epsilon, there is always an element in the set which is epsilon close to the supremum. In other words, for some n epsilon in the natural numbers, a minus an is a minus a n epsilon is less than epsilon. Okay, because this is the supremum, there is an element in the set which we are calling a n epsilon, such that a minus a n epsilon is less than epsilon. Okay, but an is an increasing sequence. An is an increasing sequence. It's an increasing sequence. Okay, what will that tell us? That will tell us that if n is greater than n epsilon, a minus an will be less than a minus an epsilon, because an is an increasing sequence. In fact, to be 100% precise, I must write less than or equal to, because it could be the case that the sequence becomes sort of constant after a while. But this is less than epsilon. Okay? This is less than epsilon. We already know that a minus an is greater than or equal to 0. How do we know this? Because a is the supremum of the set of ans. In other words, we have shown that a minus an absolute value is less than epsilon. Okay? For all n greater than n epsilon. This is just a fancy way of saying that we have shown that the definition of convergence is satisfied for an with the limit a. Right? For each epsilon, we have shown that mod a minus an is less than epsilon for all n greater than n epsilon. This shows an converges to a. Okay? Please prove the other case when an is not an increasing sequence but rather a decreasing sequence. This is a course on real analysis, and you have just watched the module on monotone sequences.